Okay, this is exam 4, physics 102, spring 18. Here we have a two-lens system. I want to split this into two pieces, so I first do this part where P1 is equal to 100 centimeters, F1 is 50, and I want to know what is M1, that's negative Q over P, so I need to know Q1, that's going to be 1 over F minus 1 over P. The inverse of that, 1 over F is 1 over 50 minus 1 over 100 to the negative 1. That's 2 over 100 minus, that's equal to 100 centimeters. And then our magnification is negative Q over P, which is negative 100 over 100. It's negative 1. So my first image is going to be 100 centimeters to the right of that first lens, and it's going to be inverted because this is negative, and it's going to be the same size as the object. Now if this distance is 100 centimeters, that means that this distance is 20 centimeters, and so P2 is 20 centimeters and F2 is 20 centimeters. Oh, we should just stop right there because this is not going to produce an image, right? If I wanted to go on and find out what Q2 is, I could. It would be 1 over 20 minus 1 over 20. The inverse, that's going to be 1 over a 0, which is going to be undefined or infinity, so there is no image formed. What causes a mirage when you see while driving on the road? That's going to be the refraction of light in warm air. It's not a reflection event. It's a refraction that if you have a warm road, we sort of did this in class, there is light rays that are traveling and they're bent in the warm air. And then you see them, but it appears as if they're coming from a reflection, like that. So that's a mirage, and it's a refraction event. When you use a magnifying glass, where do you place the specimen you want to view? Well, if you have a magnifying glass, there's your focal points. It's a convex lens. If I put my object right here, then my image is right here. It's virtual, upright, and bigger. So you want to put it inside of your focal point rather. For a given lens, what is the height of the image equal to the height of the object? Height of the image divided by the height of the object equal to. So HI over HO, that's equal to our magnification. Magnification is not an option here, but that magnification is also equal to negative Q divided by P. So these two quantities are equal to one another. So that's going to be this one, D, image distance over object distance. So make sure you get that negative right there. You stand 2 meters in front of a flat mirror. Which of these correctly give the image distance and magnification? Well, the image distance should be the same as the object distance, but negative, and the magnification is going to be positive 1. I know that's negative because this is a virtual image, and that's what flat mirrors always produce. So number 5 is A. Magnifying glass has a focal length of 20 centimeters. You hold a specimen 10 centimeters in front of the lens. What is the magnification? So here I first want to find my magnification, that's negative Q divided by P, but I don't know Q, so I have to find that. So I have 1 over F, that's 1 over 20, equals 1 over Q plus 1 over P, that's 1 over 10. So Q then is equal to 1 over 20 minus 1 over 10. The inverse, that's 1 over 20 minus 2 over 20, so it's equal to negative 20 centimeters is Q. And then this is going to be equal to negative 20 divided by P, which is 10. Those negatives become positive, and so 20 divided by 10 is positive 2, so 6 is E. Got to be careful with these signs right here. Make sure that you get both negatives, because if you miss one of those negatives, you would have put negative 2. But a magnifying glass is not an inverted image. It's always an upright image. By the way, if you weren't sure about the previous one, what was at number 4, you could look at this one and find out it should be inside the focal length. Image has a magnification of +2. Which of these statements are correct for this image? Okay, well, the image is bigger than the object, and I know that this has to be either a convex lens or a concave mirror. All right, and I know that in those, that when the image is bigger, that the image is both virtual and the image is upright. That's when you have, say, a concave mirror when the object is right here and the image is right there. So it's a virtual upright image. But if I'm not certain about that, I can look at my magnification formula, -q divided by p. And I know if this value is positive, then q has to be negative to make that positive. So that's going to be the case there. And then also, because this value is positive, it's going to be upright. Okay, so I can find out all that just from knowing my lenses and mirrors, or from just thinking about the signs of this formula. So A is 7. What is the focal length security mirror that produces a magnification of 0.5 when the person is standing 2 meters away? All right, so P is equal to 2, and M is equal to +0.5. I know it's positive. This is a security mirror. This is a convex mirror. All right, that's the mirror where you have the person over here, the object, and then you have your image over here. So I know that my image is always upright in a convex mirror, and so my magnification is always positive. So I have M equals -q divided by P. That's 0.5 equals -q divided by 2. So q, solving for that, is equal to -1. Hold on, let me make sure. I might have fixed this. No, I'm sorry, I was just not reading the problem. So here, q is equal to -1 meters, but I'm not looking for q. I'm looking for the focal length. So I need to find the focal length. I have p now and I have q. So the focal length is equal to 1 over q plus 1 over p, to invert that. And so that's going to be 1 over -1 plus 1 over 2. This is 2 over 2 plus 1 over 2. That's 3 over 2. Excuse me, that's -1/2 inverse, which is -2. So the answer should be C for number 8. All right, number 9. Mirror produces an image. The object is 8 centimeters high, so HO is 8. It's 2 centimeters to the left of the mirror, so that's P is +2. The image is 16 centimeters high, so HI is 16 centimeters. So already this should tell us something. First of all, this is a concave mirror. So because the image is bigger than the object, it's twice as big. The center of curvature of the mirror is 8 centimeters. That means that the focal length is +4 centimeters. I know it's positive because it's a concave mirror, because that image is bigger. And I want to know, where is the image located? So I want to know, what is Q? All right, I really have a little bit more than I need for this, because I need to first find the magnification, but that's easy. I can just say HI over HO. That's equal to 2. And then my magnification is equal to -Q over P. So 2 is equal to -Q divided by P, which is 2. So Q should be equal to -4, which is going to be 4 centimeters to the right of the mirror. I know that because the object is to the left of the mirror. The object is over here. That means that the image is going to be over here. Anytime I have an upright virtual image, it's going to be on that side of the mirror. A flat mirror produces an image that is virtual, upright, and the same size as the object. Which of these rays are drawn correctly? Okay, parallel to the axis and then through the focal point. Remember, it's like you trace it back and then it goes, so that one's okay. This one goes through the focal point, yes, and then it goes parallel to the axis, that one's okay. And this one goes to the center of the mirror and then back again. And then let's trace back those virtual rays. I'll do them in red. Here's one virtual ray. Here's another virtual ray. And then here's the third virtual ray. And look, they all cross at the same point. So that should be a key to tell me that all are drawn correctly. Consider this object an image. The image is inverted and on the same side as the object. What is the type of lens or mirror? Well, because it's inverted, I know that this has to be a mirror because it is a real image. It's inverted, so it's real, and it's on the same side as the object, and only mirrors have real space on this side. And the only type of mirror that does that is a concave mirror. That's number 12. That's the, oops. That's the mirror that looks like this. Which of these following describe the image from a concave lens? That's a lens that looks like this, that forms an object distance more than one focal length. Well, this doesn't really matter because a concave lens always produces an upright, diminished, and virtual image. Always, just like the convex mirror. 14, diffraction line has 2,500 lines per centimeter. What is the first order maximum with that wavelength? So first I want to find what is my distance between the slits. That's 1 over 2,500. Which is 4 times 10 to the minus 4 centimeters, or 4 times 10 to the minus 6 meters. And then I want to know what angle for the first order maximum. Wavelength is 520 nanometers, or 520 times 10 to the minus 9 meters. So I say d sine theta equals m lambda. And I solve that for theta. So it's going to be the inverse sine of the wavelength over the slit width, or the separation between the slits. I get 7.5 degrees. Describe a diffraction grating. Okay, well, first of all, it's evenly spaced. It's not randomly spaced. So it's not B and it's not C. They're evenly spaced parallel lines. So evenly spaced parallel lines, not intersecting lines. So it's not A. So we'll just go straight with D, but let's just make sure this is right. Evenly spaced parallel lines, and it produces an interference pattern that's similar to, but sharper and better dispersed than that of a double slit. So that is correct. Number 15 is D. That was straight from OpenStax. Okay, here I have two slits, double slit. I want to know how far is the second bright fringe from the central maximum on a screen that's 5 meters away. So I say d sine theta equals m lambda, 0.2 times 10 to the minus 3 sine of theta equals m, which is 2, the second bright fringe, times lambda, which is 650 times 10 to the minus 9. I solve for theta. I get theta equals 0.37 degrees, and then I want to solve for y. That's going to be L tan theta. L is 5, tan of 0.37, and I get 3.25 times 10 to the minus 2. That's in meters, so that's 3.3 centimeters. 16 is D. Young's double slit interference apparatus. What factor does the distance between adjacent light and dark fringes change when the slit separation is doubled? So I have d sine theta equals m lambda. If I double this, I have my angle theta. And since y is equal to L tan theta, if I have my angle theta, I have the distance between them. So C is the right answer for 17. Listen, you can think about this too. If I make my slits farther apart, then my fringes get closer together. And so I know that it can't be A or B. It has to be either C or D. And then it is a linear proportionality, so it has to be C. This has a double slit diffraction pattern. What's the path length difference? All right, let's see. This is my central fringe, so that's at 0. So this is a half a wavelength, 1.5 wavelengths, 2.5 wavelengths. So C is right. Two waves of 3 meters travel through space. The first travels 8, the second travels 10. When they meet, what type of interference occurs? Well, the key here is what is the difference? The difference is 2 meters. That's my path length difference. And they have wavelengths of 3 meters. So I'm not at a half a wavelength, and I'm not at a full wavelength. So I'm going to get neither total constructive nor destructive. Ambulance is moving away from you. You are standing still and you hear its siren at a frequency of 98. You know the actual frequency is 102. What is the speed of the ambulance? So for a source moving, the observed frequency is equal to the source frequency times the speed of the wave divided by the speed of the wave plus or minus the speed of the source. This is straight from OpenStax, by the way. So my observed frequency is 98 equals 102 times 331 divided by 331 plus or minus. Well, it should be plus because this number is bigger than that number, and so I need that denominator to be bigger. And then I solve that. 98 divided by 102 is 0.961 equals 331 over 331 plus Vs. So 331 plus Vs is equal to 13.4 or yeah, 14 meters per second. Number 20, let me double check that. Yeah, it should be C. All right. I rounded off here, but it should be 14 meters per second. 40 dB is how many times as intense? Well, the difference in the intensity level is 20. Right? That's 40 minus 20 is equal to 20. And a difference in decibels of 20 is equivalent to 100 times as intense. What is the intensity level? Unit, decibels. Okay, so here my frequency is 1 over 2L square root of T over mu. And if I increase the mass of the string, that's going to increase this by a factor of 2, which is going to increase my frequency by a factor of 1 over root 2. And my frequency is 320. I divide that by root 2. And I get 230. Look, you know that if I'm increasing the mass of the string, it has to decrease the frequency, so I can get rid of these options. And then it's a matter of, is it decreasing it by a factor of 2 or by a factor of root 2? And it's going to be root 2. Okay, number 24. Water break at the entrance of a harbor consists of a rock barrier with a 30-meter wide opening. Ocean waves at 10-meter wavelength approach the opening straight on. At what angle is the incident direction are the boats inside the harbor most protected against? Okay, so A is equal to 30, wavelength is equal to 10, and I want to know what is theta. So I say, oh, and I don't know what M is right off, but we're just going to pick 1 and see if that works. And if that doesn't work, then we'll choose 2, then we'll choose 3. I know that it's not going to be, you know, It'd be either 1, 2, or 3. We'll just pick one. And so 30. I'm sorry, I have to pause this for just a second. Okay, so here I'm looking for theta, so I say a sine theta equals m lambda. And I'm solving for theta, inverse sine of m lambda over a. We're just going to choose m first and see how that goes. And lambda is 10 divided by 30. So the inverse sine of 1/3. I get 19.47. 19.5 degrees. And it turns out that is an answer, so that must have been what it was. Now look, this is what's happening here. I have this break in my harbor, and I get these period places of constructive and destructive interference. So I'm going to imagine that this is light, and we'll just draw a screen here. What happens is that here, as I go along this path, I get constructive interference along that path. But as I go along this path, I get destructive interference all along this path. And then when I put a screen right here, I get destructive interference right there. So if I were to put a screen, say, right here, I'd get destructive interference right there. Or if I were to put a screen here, I would get destructive interference at that point. So all along these paths, I get destructive interference. Likewise, all along that path, destructive interference. All along that path, I get destructive interference. And that's what the problem's saying, is that you get these, periods, these places where the waves destructively interfere, and so those are quieter places. Okay, which of these shows the wavelength of a transverse wave? Well, I'm starting here. The wavelength goes to there. That is B. What is the frequency of a sound wave? Well, wavelength is 1.2 meters. The speed is 430. Speed is equal to wavelength times frequency. So frequency is V over lambda, 430 over 1.2. It's 360. Particular sound is 23 times more intense. So what I'm doing there is I2 over I1 is 23. And I want to know what is the difference in the sound intensity levels. This is equal to 10 delta L over 10. So I have to take the log of both sides. The log gets rid of that. The log of 23 is 1.36. I multiply that by 10 and I get 14. So 27 is A. So if I increase my decibel levels by an amount of 14, it increases my intensity by a factor of 23. What am I going to do this summer? Well, I am going to work some. I'm going to hang out with my family and friends. I'm going to play with our dog. I think we're going to travel. So E is the right answer. Usually if it's in all caps, that means that's the right answer. Okay, that's the end. Let me show you the answers here. Notice that there were a lot of OpenStax questions.